Hello, welcome to the series of lectures on group theory. We will start group theory from algebraic structures. Suppose you are given a set. For example, you can choose any set. Let me choose 1, 2, 3, 4, 5 up to 10. So this is a set, and if you are given a set, you can define some binary operation on the elements of the sets. For example, on this set, you can define binary operation addition. That means if you add 1 and 2, you will get new element from 3, from this set, which is 3, right? If you add any two elements of the set, you are getting some element, some new element, and that element is sometimes in this set, and sometimes it may not be in this set. For example, if you add these two things, you will get a number which is 3, which is in this set. But if you add, for example, if you have 10 here, if you add 10 and 4, you will get 14, and 14 is not in this set because this set only have 1, 2, 3 up to 10 elements. So this kind of binary operation we can define on the set. So we will say, since addition is not defined on this set, because if you take 4 and 10 and if you add them, you will get a number which is not in this set. That means you will say this binary operation addition is not defined on this set. Okay, so there are some sets on which we can define binary operations. For example, if you take A is equal to 1, 2, 3 up to so on, and it keeps on going up to infinity, then what will happen? If you add any two numbers from this set, let's say you can take 50 because 50 will come after some numbers, and you add, for example, 100 in this number, then you will get 150. And this 150 is here because these elements are keep on going. They will never end. So that means this operation, binary operation addition, is defined on this set, right? Similarly, if you want to define another binary operation, you can define it. For example, if you want to define multiplication, you can check if you multiply any of these numbers, you will get a new number which will be again in this set. For example, if you multiply 2 and 3, you will get 6, and 6 is here. If you multiply 6 and 18, you will get 108, which is again in this set, because these numbers are keep on going there. So all numbers from 1 to 3 to up to infinity, all numbers are in this set. So that means binary operation addition and binary operation multiplications are defined on this set. Okay, so what is algebraic structures? Algebraic structures is a set on which some binary operation is defined. And binary operations, previously we have shown you there are two binary operations, addition and multiplication. There are actually more binary operations. So which we will take, we will just write star. And star is the general binary operation. It can be addition, it can be multiplication, whatever. If it's not clear in the context, we will just write star. Okay, so the algebraic structure is a set on which some binary operation is defined on it, and that binary operation has some properties. So any set on which you define a binary operation and that binary operation has some properties, so with all of those properties with the binary operation, you will call that set an algebraic structures. Here are some examples. The set of natural numbers, which is just 1, 2, 3 up to so on, This set is an algebraic structure with the binary operation addition and multiplication, right? Okay, so let me do another example. This example is z, which is the set of integers, and set of integers is usually denoted by 0, 1, 2, 3 up to so on, and -1, -2, -3 up to so on. In this set, you can also define this binary operation addition. If you add any two numbers, you will get some new number inside this set. And if you multiply any two numbers from here, you will get another number in this set. So that means this set is keep on going along positive side as well as it keep on going along negative side, right? So since it never ends on the positive side as well as on the negative side, that means both of the binary operations are well defined on this set. So that means this is also an algebraic structure with respect to the binary operation addition and multiplication. So I will write these two are binary operations, are algebraic structures with these two binary operations. So if we are talking about any set, we will talk about that set together with some binary operation. For example, if you write z, if you talk about z and you talk about its binary operation multiplication, normally we write multiplication this way with dot, right? If I write this way, that means I'm defining this multiplication on z. Or if I'm writing z, comma with plus, this means I'm talking about the binary operation addition defined on z. That means this time, if I have to operate two elements of z, that means I have to add them. If I'm talking about this kind of structure, that means whenever I take any two elements from z, that means I have to multiply those elements, right? So we will use this notation to describe an algebraic structure. So similarly, you have the set of real numbers denoted by r. It is also an algebraic structure with the binary operation addition as well as with the binary operation multiplication. But yeah, so we have another group, you can call it q, which is the set of rational number. This is also a binary an algebraic structure with the binary operation addition. Similarly, you can have the set of complex numbers with the binary operation addition. They are all algebraic structures, right? So we need to study some properties which are common in all of these structures. And so for time being, I will rule out this algebraic structure from here because this is not nicer one. So we will study those properties which are common in all of these algebraic structures, and we will name those properties. So the very first property is closure property. Some people call it internal processing. So what is this property? This property states that let V is a set. Let me write V as an algebraic structure. Let V together with the binary operation star is an algebraic structure. then this operation star is called inner operation, or we say that, or the same thing, we say that this set V is closed under star Some people write V is closed under star, and some people write star is called inner operation. So these two statements are the same, they have the same meaning. Yeah, so V is closed under star if for every two elements x and y of V, that means if you pick any two elements from the set V, then x star y must also belongs to V. If this property satisfies, then we say that the star is inner operation, or we say that V is closed under star. Okay, that's why it is called the closure property. That means V is closed under star if for every two elements, for every pair of elements in V, the new element after the operation of these two elements x and y, the element which you get after the applying this operation, that new element is also in V. Here are some examples. This is the set, right? So can I say that A is closed under plus? You can define an operation addition on it, right? You can, it's up to you. There are two common operations which are used here. Okay, your star can be either plus or it can be multiplication. So for example, you take star to be plus, this set A is not closed under addition. Why it is not closed? Because okay, if you add 2 and 3 you will get 5, right? If you add 2 and 3 you will get 5, and this 5 is inside this set. If you add 3 and 4 you will get 7, right? And 7 is also in this set. Does this property hold for all elements of A? That means, can you say that for every two elements of A, x plus y is in A? Can you say? Can you say that for all x and y belongs to A, x plus y belongs to A? This is true or no? Think for a moment. I think you must come to know that this is not true, because if you take 10 and 15, both are here in this set. If you take 10 and 15 from A, then what is 10 plus 15, which is 25, right? Now let's look. 25 is here? No, of course no, because this set only contains from 1 to 20, only first 20 elements. This is equal to 25, which is not in A, right? It is not in A. This means it is in A, but this means it's not in A, right? Since this property must be true for all x and y, but this property was not true for all x and y, we have found two elements in A whose sum is not in A. So that means A is not closed under addition. In other words, you will say addition is not an inner operation, because for inner operation it must true for all elements that if you add all elements together, you do not go outside of A, right? So you will say star is okay, addition is not inner operation. In A. Look at another example. If I write the same set, but you know where the confusion came, because this set stops, right? If I don't stop, if I write a set, if I don't stop at any point, if it keep on going, then what will happen? Let just the case for the set of natural numbers 1 2 3, it keeps on going. These numbers keeps on going and never stop. Then what about plus? Plus is binary operation on A or no? In other words, plus is an inner operation on A or no? My claim is yes, it is inner operation for n, because if you add any two elements from here, if you take any two elements from here and if you add them, after addition you will get some new number which will be inside, because this set never ends, it keep on going, it never ends. For example, if you add 100 and 200, you will get 300. If 100 is here, 200 is here, 300 will be here. That means all elements, if you add any two elements, you will get new element which will be still here. Okay? Because for all x and y belongs to A, what does that mean? Not A, belongs to the set of natural numbers, because I am talking about the set of natural numbers. For all x and y means for all any two elements. I cannot take any example. We know that x plus y is also a natural number. If you add any two natural numbers, that means you are getting again a natural number, right? Therefore n is closed under addition. Therefore we say star is inner operation for A, for n, or we say n is closed under addition. Okay, so for this set we have proved that addition is an inner operation for n, right? And similarly for the same set you can prove that multiplication is also an inner operation for this set, because if you multiply any two natural numbers, you will get a new natural number which will be above, which will be here in the set, right? But after some numbers. But if you talk about this set, This set is also not closed under multiplication because if you multiply, for example, 10 with 3, 10 and 3 both are here. Here you have 10 and here you have 3. If you multiply them, you will get 30. 30 is not here, right? This means this set is not closed under multiplication. It is not closed under addition. But if you take this set, this is nicer set because it is closed under addition also. It is closed under multiplication also, right? So this set is nicer structure. So your assignment is to find more sets which are nicer. Nicer set means those sets which satisfies these properties. This property, closure property, right? So I claim that these sets which I have defined above, these sets have closure property with respect to addition, right? So you have to find more structures, more sets. So let me define another property. So the second property is, again, let V is a set and star is the binary operation. So whenever we will talk about set, we will talk about the binary operation, right? So V is a set and star is a binary operation. So these two things together, they are algebraic structures. Then star is called associative. Previously, we defined closure. Star is called closed or inner operation. This time we call associative if. So this property relates three different elements. Previous property was relating two different elements. Look here, this property, inner operation, it was satisfying for only two elements. It was relating only two elements. It says if you have two elements from the set, then their operation is also in the set. If you are able to find any two elements in the set such that their operation is not in the set, that means you will say this property does not hold. But what is this property? It says if for all three elements x, y and z belongs to V, we have x star y star z is equal to x star y star z. That means if for any three elements this thing is equal to this thing, this means star is associative, right? You will say star is called associative if for every three elements this is equal to this. What is meant by this and what is meant by this? Here, this means if you operate y and z first and then you operate x with the result, or if you operate x and y first and then you operate the result with z, you will get the same answer, right? That means on this side of the equation, you are operating these two first, but on this side, you are operating these two first. That means operating any two elements first does not change our answer. This is called the associativity, but it is not true every time, right? It is not true for all the binary operations. It is true for some of the binary operations, right? Here are some examples. If you take any set, for example, if I take 1, 2, 3, for example, up to 20. Okay, let me take any three elements, right? Because associativity, for the associativity, you need to take three elements, right? For example, you take 3, 2, 3, and 5, right? And the binary operation, whatever you want, you can have any binary operation. For example, if you want to take addition, you can take, it's up to you. So I want to take addition. So if I add these two first, or if I add these two first, what do you think? What will happen? Will I get the different answer for both, or I will get the same answer? Let me check. If I add these two, here I will get 8, right? And here, then I will have this one. If I add these two first, what will I get? This is 5, and this is what? This is also 5. Here you have different numbers, but if you add these two, you will get 10. If you add these two, you will get 10 again. So surprisingly, you are getting the same answer, right? Okay, so this means star is binary operation, star is associative here on this set. For this set, star is associative, not star. I am talking about plus because I have added things. So you will say plus binary operation addition is associative. Right? And this is not only true for these three numbers. If you take any three numbers from here, if you add these two first or these two first, you will end up with the same answer. I mean, on this step, you will have the different numbers, but when you add them, you will get the same answer, right? You can check for any three numbers from this set. Okay. Let me give you an example on which the binary operation is not associative. If same set, if you take same set, but the binary operation is minus this time. Previously, the binary operation was addition, but this time is minus. Let me check if this binary operation minus is associative or no. Let me check. Let 2, 3, and 5 again. 2, 3, and 5. So this time binary operation is minus. So I will write minus here, okay? Minus here and minus here. This means if I subtract these two first or I subtract these two first, whether I get the same answer or different one. Let me do that. 2 minus 3 minus 5 is what? 3 minus 5 is minus 2, right? And here I don't know they are equal or no. So 2 minus 3 is minus 1. And this is minus 5 as it is, right? But if you take this minus and this minus plus, you will get 2 plus 2. And here you will get minus 1 minus 5. This is 4. I don't know, they are equal. This is 4 and this is minus 6. Are they equal? They are different, right? So you will say minus is not binary operation, is not associative on the set A. Okay? Now let me define another property. Again, if V is an algebraic structure and if there is an element, we call this element E. This is the notation for this element. Belongs to V such that E star x is equal to x star E is equal to x for all x in V, then E is called the identity or the neutral element. What is meant by this? If this is an algebraic structure, if you are able to find an element inside this V, you can call it E. If there is an element such that if you operate that element with x from the left side or you operate that element with x from the right side, you will get only x. That means that element has no effect, right? This means if you operate this element with x, you are getting back x. That means this element has no effect. And it has no effect from the left side as well as from the right side. So from any side it has no effect. That means this element is neutral or the identity element, right? Here is an example. If you take the set of natural numbers 1, 2, 3, 4, 5, 6. Okay, we will talk about first the binary operation multiplication. Let multiplication is the binary operation. So whatever the set is given, and if you want to check any property, you have to first check what is the binary operation. If you have decided the binary operation, then you will talk about any property. Otherwise, you can't talk about any property. So, can you find any element in this set such that if you multiply that element with any element, you will get the same answer? For example, 2 is in the set of natural number, right? But this identity is such element, if you multiply identity with anyone, you will get that element back. For example, 2 is not satisfying this property. Why? If you take, for example, 3 from n, then what is 2 times 3? Are you getting back this thing? No, you cannot get this. You will get 6. So that means 2 is not playing that role, because that role means if you multiply E from the left side or from the right side, you will get no effect of E. But here in this example, 2 is leaving effect on 3 because 3 got changed after multiplication with 2. So 2 is not that number. Can you find any number? Look, if I write 1 here, what will happen? If I multiply 1 with 3 from the left side or from the right side, I will get back 3. That means this one is neutral, because if I multiply from the left side or from the right side, I will get no change. And you can take any element from here. If you take here, write 10 or 10, you will get back 10. So 1 is a number such that for any number, here if I write any x, and here I write any x, here I write any x, I will get back that x, because 1 times x is always x. So for this set, 1 is neutral element with respect to multiplication, right? Okay, here is a question for you. Does the same set have identity element with respect to addition? Here is the question. So this is my question. Does n have neutral or identity element with respect to the binary operation addition? Here is the natural number. If you take, for example, 1, if you add 1 to any number, that means that number will get changed. For example, if you add 1 to, for example, into what? For example, here if you write 2, can you get back 2? You can't, because here you will get 3, right? But if I add here, for example, 10, I will get 11, right? So, my claim is, can you get here a number? If you add into 10, you will get back 10. The obvious answer is 0, right? Only 0 satisfies this property. But 0 is not here, right? That means this set has no identity with respect to addition, because only 0 was the number which satisfying this property, but 0 is not here, so that means this set doesn't have identity with respect to addition, right? So the answer is no. So come to the last property. This property says if V is an algebraic structure, then we say that any x belongs to V has inverse with respect to the binary operation star if there exists y belongs to V such that x star y is equal to y star x is equal to identity. What does that mean? We say that an element from V has inverse if there exists another element y such that if you operate x and y, you will get neutral element identity. Here is an example. If you take this set 0, 1, 2, 3 up to so on, minus 1, minus 2 up to so on. So we need to check this property. So for this property, in order to check this property, we need to define some binary operation here. So which binary operation should I define? I should define the binary operation addition. Let addition is the binary operation, right? Okay, if we have decided a binary operation, now we have to find its identity. What is the element inside this set such that if you add, because the binary operation is addition, if you add that element with anyone, you will get no change. Can you check it? The obvious answer is 0, because if you add 0, for example, with 3, you will get 3 plus 0, which is 3. That means 0 has no effect if you add. Okay, the identity element is an element which has no effect if you operate. Here the operation is addition, so that means 0 has no effect if you add it, right? So 0 is identity. So here E is 0, right? So here identity is 0. Okay, so we have to check for any x, can you find another element y such that if you operate them, you will get neutral element? So for example, for 3, let 3 belongs to Z. Can you find an element in Z such that if you add, because you need to find an element from V such that if you operate them, you will get identity, right? Can you find an element in Z? What is that element? I don't know, such that if you add that element in 3, you will get identity, which is 0. So the obvious answer is minus 3. And minus 3 is here because here you have minus 1, minus 2, minus 3, right? So the obvious answer is minus 3. So for 3, you have minus 3. For 1, what is that element? For 1, the inverse is minus 1. Okay? Because this kind of y is called inverse, right? We say x has inverse if there is y. So that means x and y are inverses. So here, if the binary operation is addition, you will say 3 and minus 3 are inverses. 1 and minus 1 are inverses because if you add 1 with minus 1, you will get 0, which is identity. 2 and minus 2 are inverses, right? So this is the concept of inverses. So if you have a set which satisfies all of the properties, here is conclusion. If V satisfies property 1, 2, 3, 4, which I have defined above, then V is called group. With respect to the binary operation star, here are some examples of group. Set of integers with respect to the binary operation is a group. You can check this set has all properties, 4 properties which I have defined. You can check. Another example is set of rational numbers with respect to addition is also a group. Set of real numbers with respect to addition is also a group. Set of natural numbers with respect to addition is not a group, right? So these are some examples. In the next video, I will explain them.